Hello. In this video, we're going to learn about tangent lines and tangent planes in multivariable mathematics. But to begin, I'd like to start by reviewing tangent lines in two-dimensional calculus, or in a Calculus 1 course. In general, we know that the equation of a line requires two pieces of information, usually either the slope of the line and a point on that line, or it requires 2 points on the line. From the 2 points, you could then calculate the slope between them, and you'd usually write the equation of a line in point-slope form. So, back in calculus, we often are presented with this situation. In Calculus 1 course, we've got an xy axis, and we've got some function. Y is a function of x. And so this is in Calculus 1. And you have the graph of some function. Maybe it's something like a parabola. And then you want to find the slope of that function at a particular point. Maybe you want to find the slope of this function at this value of x. So what you do is pick another value of x, which is a little bit larger. Let's call it x plus h. And to each of those values of x correspond a value of y, and you get 2 points on the line. And then you can calculate the line which goes through those 2 points. And one of the main ideas in calculus is that as you let h get closer and closer to 0, these 2 points move closer to each other, and the line that passes through these 2 points, which is called the secant line, that line gets closer and closer to the tangent line which is tangent to the graph, passes through at only 1 point. So that's the idea in Calculus 1. Now, in multivariable mathematics, we have functions of more than one variable. Right? So we want to discuss a similar situation. And so I'm going to go ahead and try to draw a picture. Okay, so let's say in multivariable math, right, we might find ourselves dealing with the following situation. We've got a three-dimensional situation. And so maybe I'll make this the x-axis, the y-axis, and the z-axis. And we're given some function. Maybe z is a function of x and y. And so f is a function with 2 input variables and 1 output variable. And then we've got the plot of some function. So we think of z as being the height. I'll draw the only 3D function I can. It's supposed to look like a hill. What I'd like to do is calculate the tangent line to this surface. It's not just a curve, but it's kind of a two-dimensional curvy surface. But there are, in fact, lots of tangent lines for this equation. And so, for example, let me change colors and let me actually choose a point on this function. Maybe we're interested in a point, like say about here. If there's lots of lines in three-dimensional space which are tangent to the surface at that point. And I'll draw a few of them for us here. All right, so first, let me draw your attention to the x-axis, which I'll go ahead and color in red. And one thing you could do is fix a value of y and then let the x value vary. right? And then you'll get some kind of a tangent line, maybe something like this. And so we let x vary. It's variable, huh? And then treat y as a constant. In this case, we'll get a tangent line, which is parallel to the x-axis. And so we'll find a tangent line. Let's say going in the x direction. Right? And what we're basically doing here is, again, it looks like we're calculating the slope between 2 points, if you think about it. You might pick another point on this surface, and you might be calculating the slope between those 2 points. Right? This first point here, maybe that's x comma y, an actual point. This other point up here, the graph gets really complicated fast. That's x plus h comma y. And so it's a nearby point, just a little bit further out in the x direction. If I want to calculate the slope between those 2 points, right, what would I do? I would calculate f of x plus h comma y minus f of x comma y. That would give me the slope, or not quite yet. And I'll do x plus h minus x. And that's like a slope formula. In this case, we're calculating the difference in z over x. Right? So this is how fast is the z component, or how fast is the height of the surface changing as x changes. And normally what happens is we have a positive x and a negative x. So we cancel out all the things that we can. And we're just left with an h on the bottom, which I'll go ahead and rewrite. And as those 2 points move closer and closer together, we're taking the limit as h goes to 0. What we're calculating is, in fact, the partial derivative with respect to x. I could write that as df dx. We could also think of it as dz dx. So that will give you the slope of a tangent line in that direction. Now, you could do the same thing for the y component as well. I don't want my diagram to get too messy, but let me go ahead and draw your attention to the y-axis. And similarly, right, you could calculate a tangent line parallel to the y direction. And going through a similar process, the slope of that tangent line you could calculate as a partial derivative with respect to y. Now, it's kind of hard to visualize things from these graphs. So next, I'd like to go ahead and call up a website, which I put together to help us kind of visualize what's happening here slightly more easily. All right, so right here, we have an interactive 3-dimensional surface. And here, I've color-coded the axes. So the origin is kind of hidden by this surface. It's somewhere in the middle. I could temporarily hide the graph here. And so there's our 3 dimensions. Right? The x-axis I typically like to render in red, the y-axis in green, and the z-axis in blue. Let's turn that back on. And what I would like to do is calculate tangent lines at some given point. So this point right here that I'm currently highlighting, so it's hard to see, it's half hidden by the graph. This is the point where x and y are both equal to 1. So I'd like to calculate the slope. And again, there's multiple slopes. But first, let's calculate the slope in the x direction. So I've rotated the graph. The x direction is going from the lower left of your screen to the upper right. So again, the way I think about this is x is allowed to vary and y is being held constant. So I'm going to go ahead and add a plane, right, a light red transparent plane here. And this plane, you might notice, it's going through, it's perpendicular to the y-axis, right? So this is the set of points where y is equal to some constant. In this case, y is equal to 1. X and z are both allowed to vary. Y is equal to 1. Now this plane, it intersects the graph in a certain curve, which I'll go ahead and highlight in red. Right? And what this curve is showing us, think of this as a cross section. Right? And let me temporarily turn off the graph. Right? For this fixed value of y, right? This graph intersects the y-axis at y equals 1. As y is equal to 1, right, you can change values of x by going left to right. And so for y equals 1, for each value of x, these are the corresponding values of z. And by holding y to a certain constant value, this is the graph that we're going to get. Now, if this is just, we think of this as a calculus 1 problem, so let's look kind of straight along the y-axis here. Right, we could calculate the slope of this curve at this point. That's just kind of a calculus 1 style problem. Right, and what we'll get is here's part of the tangent line right here. But now we'll remind ourselves that we're in a three-dimensional problem. And let's reintroduce the 3D graph. So what we have here, this little red vector that's appeared, this red vector is tangent to the surface along the x direction. Go ahead and hide the plane here. And so this is kind of a visual indication of what the partial derivative is telling us geometrically. Now you could do the exact same calculation for partial derivatives with respect to y. And so again, at this particular point, you could fix a value of x. Again, let's fix x is equal to 1. And this light green plane here, right, this intersects the x-axis at x equals 1. Right, we can kind of see that from this perspective. And so this is the set of points that we get when we allow y to vary and we treat x as a constant. And again, we'll get a cross-section of the curve. It looks like the other cross-section because this is a highly symmetric graph. Right, for fixed x values, these are what the y values are going to look like. Once again, we can calculate a derivative, right? The partial derivative in this case will be this vector right here. Right? As y is changing, z is also changing. In this case, z is sloping downwards a little bit. So again, putting the original graph back on. Let's temporarily hide these things, but leave the derivative on. Let's bring this back into view. Right? This green vector down here is also tangent to the surface, going in a y direction. So in fact, we've got two different tangent vectors at this point, an x derivative and a y derivative. In fact, there's other directional derivatives as well, which we'll talk about at another point in time. But here we've got ourselves two tangent vectors. Now, how can we use these to come up with the equation of a tangent line? So we're going to go ahead and head back to our virtual whiteboard here. And so our next step is going to be to use partial derivatives to calculate tangent lines. So our goal is going to be to use partial derivatives to calculate in particular parametric equations of tangent lines. Right. So what's the idea? Well, you might recall that the equation of a line in 2 or 3-dimensional space, I often like to write like this. The function L of t, I put a vector above the L to indicate that it's a vector valued function. I like to write this as vector m times t plus p, where m I think of as a slope vector. That gives us the change in x, change in y, and change in z. And p is a point on the line. And so, for example, you might have the equation, right, this is 1, 2, 3 times t plus 2, negative 1, 4. Perfectly good equation of a line. Now, how do we calculate the slope vector if we start off with a multivariable function? Right, so given z is a function of x and y, the big question is, how do we find calculate value of m at a given point? The answer is, of course, we're going to use some calculus. Let's go to the next page. So let's come up with a simple example. Now, let's say we have z is a function of x and y. Something like, let's try x squared times y cubed. And we want the tangent line. Oops. Like the tangent line at, say, xy equals 1, 2. Right, so we need 2 pieces of information to write the equation of a parametric line. We need a point on the line as well as the slope of the line. Right, to find the point P, right, this is a point in 3-dimensional space. We have our x value, we have our y value. How do we get the z value? Well, remember, we have an equation for z in terms of x and y. So to get the point that we're going to need for our equation, we would calculate f of 1, 2. And so we're just going to plug 1 and 2 into this equation. So I'll have 1 squared times 2 cubed. So that will give me 8. Right. 1, 2, 8. It's going to be the point that we add on at the end of our parametric equation. So next, let's see. Maybe I'd like to come up with the slope of the line. Right, the slope of the line, remember, that's going to represent our change in x, change in y, and change in z. Think of this as delta x, delta y, delta z, or when we calculate slopes in 2 dimensions, we usually think of delta y as the rise and delta x as the run. So rise over run. If I may be so bold to introduce a new term for delta x in this context, I'd like to think of that as the raise. Right, so run across the x-axis, rise in the y, and then raise. Think of this as raising yourself above the xy plane in 3 dimensions. Plus, I like that these all begin with the letter R. They have 3, 4, and 5 letters respectively. Right, how are we going to calculate these different changes? Well, changes are measured by derivatives. Right, and so in particular, the change in z, the change in the height, that's measured by dz dx. In the case, I need to make this clear right away, this is for a tangent line in the x direction. And we're going to get a slightly different formula for tangent lines in the y direction or in other directions. And so when we're calculating the slope vector, the last component, the raise, is going to be the change in z as we go along the x direction. That's why we have the delta x down here. This delta x is because we're interested in the x direction. Now, what should we put in for the other 2 components? Well, by analogy, we're interested in how much each of these quantities change as we change the value of x. So the first component is delta x over delta x. And the second component, or dx over dx, the next component is dy over dx. And some of these things are actually pretty easy to calculate. In particular, this first component right here, dx over dx, well, that's just 1. Right? The rate of change in x as x is changing is 1. The last component, this will require a little bit of calculation, not too bad. And the answer to the middle component is pretty easy, but we want to understand why it is what it is. Right? So here, we're looking for change in y as x is changing. However, y is not a function of x. Y is an independent variable. Right? So a change in x has no effect on y at all. How much does y change as x is changing? It doesn't. It's an independent variable. So the central component is actually 0. That's it. Now, once we want to get the actual number, which goes in this last spot here, we need to calculate dz dx for this example. So dz dx, in this case, we think of x as the variable and y as a constant. So we're really calculating the derivative of x squared times a constant, and that is 2x times y cubed. We're also specifically interested in the tangent line when xy is equal to 1, 2. So I'm going to take this formula for the derivative, then I want to evaluate it, which we sometimes indicate with a little line down here. I want to evaluate this when xy is equal to 1, 2. And so I'll go ahead and plug 1 and 2 into the derivative. Then I'll have 2 times 1 times 2 cubed. That's 16. And so dz dx is equal to 16, which means that our slope vector, right, in the x direction at this particular point is 1, 0, 16. And now we have enough information to put together the equation of the tangent line. And I should always say which direction it's going in. So this is the tangent line in the x direction. So since we have that information, I'm ready to put together the equation of the line. Right? It's the slope vector times t plus our point. We have all the information we need. That's 1, 0, 16 times t plus the point on the line, which is 1, 2, 8. And that's the equation of the tangent line to the surface in the x direction. However, we should keep going. We should also come up with the equation of the tangent line in the y direction. So going on to the next page, right, so let's calculate the tangent line, again, to the same function. C is x squared times y cubed at the values x, y equals 1, 2. This time let's do it in the y direction. Right. As always, we need two pieces of information to put together the equation of a tangent line. We need a point on that line and the slope of the line. And so for the point, fortunately, these are the same x and y values that we had before. And we plug those x and y values into our equation for z to calculate the z component. But just like last time, the answer is 8. So our point is 1, 2, 8. Next, we need to calculate the slope vector in the y direction. Again, this time we're going in the y direction. What happens to x, y, and z as we're changing y? How much do each of those values change? And so in this case, what we're going to be calculating, remember, this is the slope in the y direction. It's information we need to have before we start to solve this problem. Right, again, we're looking for change in x, change in y, and change in z, but this time as y is changing. And as before, some of these are quite straightforward to calculate. One of them involves a little bit of calculus. For example, in the second component, we have dy divided by dy. It's definitely 1. And the first component, we're looking for the change in x as y changes. But again, in this case, we're holding x constant. Right? We're interested in change in y. So x being held constant, x does not change. The change in x is 0. And since x is 0, in this case, dx dy is equal to 0. Finally, we have dz dy. And this is the one which requires a little bit of calculus. So this is going to be the formula for the slope vector when we're calculating tangent lines in the y direction. So for this specific problem, we need to go ahead and calculate dz dy. So this means that y is our variable and we're holding x constant. So here, remember x is constant. We have a constant squared, which is still a constant times y cubed. The derivative of a constant times y cubed is the constant times 3y squared. Actually, I'll just move the 3 out to the front. So we have 3x squared y squared. That's our partial derivative with respect to y. Next, let's plug in the values for x and y, 1 and 2. And this tells us that the derivative, see, is going to be 3 times 1 squared times 2 squared. So that's 3 times 1 times 4, that's 12. So this is how quickly the height is changing as we change y at this point. With this information, we now know that the slope vector will be 0, 1, 12. And now we have a point on the line and the slope of the line, so we're ready to write down the equation of the tangent line. So the tangent line, and equations of lines in general, have the form slope vector times t plus point. So in this case, we have 0, 1, 12 times t plus the point 1, 2, 8. And so that is the tangent line in the y direction for this function at this point. All right, that was a good example. Let's go ahead and let's do another one. Maybe I'll start off with a new color. So again, we're calculating tangent lines to a multivariable function at a given point. So now for this next problem, let's say we're going to calculate the tangent lines in both the x direction and the y direction. In the y direction. And in this case, our function is going to be z equals, let's try maybe 3x plus square root x times y plus y squared at the point xy equals, let's see, something that'll work out nicely. Let's maybe try 4, 3. Right. For both of these tangent lines, we're going to need the point on the line. So the point on the line is going to be p equals 4, 3, comma f of 4, 3. Of course, f is the function that gives us z. So if I plug in 4, 3 here, what will we get? We get 3 times 4, which is 12, plus, we'll add 4 times 3, that's 2 times 3, which is 6. 12 plus 6 is 18, plus 3 squared, that's 9. So 18 plus 9 is 27. Right, so that's 12 plus 6, which is 18, plus 9, which is 27. Sounds good. All right, so there's the point on the line. Next, to calculate the slope vectors in each case, we're going to need the partial derivatives of this function. This is the fun calculus-y part. So the partial derivative with respect to x will be, let's see, first the derivative of 3x is 3, because x is the variable. Next, let's see, I'll have square root of x times y. And remember, y is a constant, since x is the variable in this problem. And so the derivative of square root x is 1/2 x to the negative 1/2 by the power rule. Or we can write that as 1 over 2 times the square root of x times y. Y is like a constant factor. Plus, y squared, and it's tempting to just say, oh, the derivative of y squared is 2y. But remember, x is the variable, so y is a constant, y squared is a constant. The derivative of a constant with respect to x is 0. And so that's that derivative. And then we'll calculate that at the point where xy equals 4, 3. I use this symbol for evaluating a function at a point. So it's going to be 3 plus 1 over 2 radical x is going to be 1/4 times 3. That's 3/4. Or if you'd like to put everything on a common denominator, which you might as well do to make our functions look easier, 3, of course, is 12/4, so this is 15/4. Next, let's calculate the partial derivative dz dy. Remember, this is with respect to y now. Y is the variable, and we'll treat x as a constant. And so our first term, 3x, since x is a constant, the derivative of 3x is 0. And over here, square root of x times y. Again, x is a constant in this calculation, so square root of a constant, still a constant. Looking for the derivative of a constant times y. Derivative of a constant times y is that constant. Plus the derivative of y squared with respect to y, that's 2y. Once again, we'll evaluate this when x comma y is equal to 4 3. And so square root of 4 is 2. 2 times 3 is 6. 2 plus 6 is 8. All right, this will help us put together our slope vectors in each case. And so now finally, the tangent line. And so for the x direction and the y direction, and we can get both of these going in parallel, L of t is equal to the slope vector times t plus the point, which we know is 4, 3, 27. For the y direction, we'll have a different slope vector times t plus the point on the line, 4, 3, 27. The slope vectors, well, they change a little bit depending on which one we're interested in. For the x direction, it's 1, 0, and then dz dx, which is 15/4. For the tangent line in the y direction, it starts off as 0, 1, and then dz dy, which we know is 8. And there we have it. We have equations for tangent lines in the x direction and the y direction. Now, while we're talking about these topics, there's one more thing which could go in a separate video, but kind of is so closely related to what we're doing now, it seems like we should just keep talking a little bit longer. Right? The idea is that there's lots of tangent lines, and when we're doing multivariable mathematics, we have a lot of concepts that were familiar to us from Calculus 1, but they all kind of go up a dimension. In particular, I'm going to go back to this 3D graph that we were looking at before. Right? And so since we have functions of x and y, we have, for example, 2 different derivatives we can calculate. In fact, there's lots of different vectors which are tangent to this surface at that given point. Right? So, for example, this orange vector which has just appeared, take that vector, and there's really like lots of different versions of that vector, which are all still tangent to this surface at this point. Different combinations of these 2 tangent vectors will still remain tangent. So what we actually have is something called, actually, let's take a look at this black vector right here. I can go ahead and I can spin this vector around. Right? All these different vectors are all tangent to the surface at this point. So in multivariable calculus, multivariable mathematics, what we have is more than just a tangent line to a surface. We have something called a tangent plane. Right? So this gray plane, which has just appeared, is tangent to the surface at this point. See if I can zoom in a bit. And so we're looking at it from the side here. And navigating in 3 dimensions is, well, it's tricky. But this surface, right, touches the graph in just one point, and any vector on this gray plane is going to be tangent to the surface, to the multivariable equation we have set up. Right, so this is called a tangent plane. How can we calculate a tangent plane to a surface at a point? This actually very naturally builds on what we were just calculating. So next, I would like to talk about tangent planes to a surface at a given point. Let me go ahead and switch colors. So the tangent plane to a surface, z, equals f of x comma y at a given point. So this is x comma y equal to some constants. Oh, let's not call them a and b. I'm about to use those letters for something else. Let's maybe call them. Sometimes picking letters is hard. Let's say R and S. And so if someone gives you 2 values to plug in for x and y, can you calculate the equation of a tangent plane? Well, in general, the equation of a plane, one very nice way to write it is in the form ax plus by plus cz equals d. Right, and that's the general equation of a plane. And you can think of a, b, and c. If you gather them into a vector, that gives you kind of a way of indicating the slope indirectly. This is sometimes called the normal or perpendicular vector to a plane. Normal or perpendicular vector to a plane. And so, for example, if this is our plane, which I like to draw as, think of this as a sheet of graph paper, which is being inclined and tilted at some angle in 3-dimensional space. And so there's some vector. This is the vector n. It's equal to a comma b comma c. And this vector is perpendicular to the plane. Right, so if you had any other vector in the plane at this point, it's going to be perpendicular to this normal vector. Now to calculate the equation of a plane, well, again, you need, well, there's 2 ways to do it. So to find the equation, just as was the case with tangent lines, there's 2 main approaches you can use to figure this out. You could say, if you have the normal vector and a point on the plane, then you could calculate it. Right? The normal vector gives you the values of a, b, and c, and then you could plug in the point for x, y, and z to calculate the value of d for your equation of the plane. Right? So to find the equation of a plane, you could do it from those two pieces of information, or you could also calculate the equation of a plane from 3 points. And if we were doing equations of lines, you would only need 2 points, because from those 2 points, you could calculate the slope vector and then use the slope vector in 1 point. Here, since we're talking about equations of planes, from those 3 points, you could calculate 2 vectors lying in the plane and do the cross product of those 2 vectors to get the normal vector. Right, so from those 3 points, you could then calculate the normal and then use one of the points to find the equation of the plane in this form. And so here, again, given the function which defines a surface, how can we calculate this information? Right, and it turns out, we could just plug in, 3 random points, but then we'd get, I don't know, the secant plane, for lack of a better word. We really want a plane which touches the graph in just 1 point. What we're going to do is build upon what we just learned and use the tangent vectors at a point to help us calculate the normal. And so this is the big idea. We're going to use the tangent vectors. So we're going to use 2 tangent vectors. Typically, we're going to use those in the x direction and the y direction, right, which we just calculated. To calculate the normal vector. Right? This is going to be our big plan. So first, I will again attempt to draw a picture of what we're about to do. Let me go ahead and change colors. Right, so here's the idea. Again, I'm going to draw a 3-dimensional set of axes. Let's think of this as the x, y, and z axes. Let's say we have some kind of a 3-dimensional graph. So I'll draw it like so. Right? And we have calculated, let's assume that we've calculated some derivatives at a point. So the x direction, let's say I'm interested in the tangent at this point right over here. And so maybe we've calculated the slope of the tangent line in this direction. There's our first slope vector. Involves dz dx. Then let's consider the y direction. Say we calculate another slope vector going in this direction. What we're going to do is calculate the cross product of these 2 vectors. And so this vector n is going to be perpendicular to both of these vectors. And if I give these vectors a name, for instance, let's call the slope vector in the x direction v, and the slope vector in the y direction, let's call that w. To calculate the normal vector, and calculate that as v cross w. And then, provided we know the value at this point right here, once we have the normal vector, we're going to be able to write down the equation of the plane. with this information. Right, this is the goal. So let's start off by maybe reusing one of our examples from before. And so for example, previously in this video, we took a look at the function z is equal to x squared y cubed. Right, we're interested in the point p is equal to 1, 2. Those are the x and y values. By plugging them into this equation for z, we found out that z was equal to 8. And then we had our two slopes, right, the tangent vectors. Right, we have two of them. In the x direction, we had, again, I'll just call this v. That was 1, 0, 16. In the y direction, that tangent vector was 0, 1, 12. Now, what I'd like to do here is calculate the normal vector, that is the cross product of these two vectors. And so the normal vector n, and so this is new, maybe I'll switch colors again. And we're calculating this vector in purple. So I'll switch back to purple. The normal vector is the cross product of v and w. And I can calculate that with this matrix-based mnemonic. I'll put v on this first line here, sorry, v on the second line, 1, 0, 16, and then w is 0, 1, 12. And that vector is going to be something times I plus something times j plus something times k. And so let's see, something times I minus something times j plus something times k. And for I, ignore column I, we can have 0 times 12 minus 1 times 16. That's negative 16. See, for the coefficient of j, and so ignore column j. Again, I'm doing a determinant here. 1 times 12 minus 0 times 16. So it's going to be 12. Don't forget that negative sign there. Then plus something times k. So ignoring the numbers in column k. This is nice. 1 times 1 minus 0 times 0. So this vector is negative 16, negative 12, 1. Right, so this vector is perpendicular to the graph at this point. Let's make a little note. It's perpendicular to the graph of this surface at P. Now, what do we do with this information? Negative 16, negative 12, 1. And so the normal vector again is negative 16, negative 12, 1. That's like the ABC in the equation of a plane in general form. We also have the point, P equals 1, 2, 8, that we calculated before. And we know the equation of a plane is AX plus BY plus CZ equals D. So we'll just substitute some things in. So I know the values of A, B, and C. This is negative 16x minus 12y plus 1 is equal to D. To find the values of D, we can just plug in our point. So we'll get negative 16 times 1 minus 12 times 2. Oh, I forget a Z up there. Plus 1 times 8, which is 8, is equal to D. So we have negative 16 minus 24 plus 8. See, minus 16 minus 24 is negative 40. Negative 40 plus 8 is negative 32. And so we have our value for d, that's negative 32. So our final equation for the plane is negative 16x minus 12y plus z equals negative 32. Or if you don't like all those negative signs, you could just multiply both sides by negative 1. And we get 16x plus 12y minus z equals 32. And that's the equation of the tangent plane. And a few things are worth pointing out here. There were some very nice simplifications that happened when we were calculating the normal vector. I want to point out that these aren't coincidences, that we should expect some nice simplifications to occur every time we do this calculation. And so here, let's make a couple of notes. Maybe I'll switch to a dark blue. So notes on calculating the normal vector n. Right? We're going to use two tangent vectors to calculate n. And you might recall that those vectors that we're going to use, right, the tangent line in the x direction was dx dx, dy dx, dz dx, which always simplifies to 1, 0, dz dx. Similarly, we used the tangent line in the y direction. So that is dx dy, dy dy, dz dy, which nicely simplifies to 0, 1, dz dy. And so as we calculate the normal vector, as v cross w, that's always going to look like this expression, no matter what the function, 1, 0, dz dx, 0, 1, dz dy. And so what are we going to get here? It's something times I minus something times j plus something times k. And the coefficient of I is going to be, let's take a look at this. And so ignore the column of y. We've got 0 times dz dy minus 1 times dz dx of minus dz dx. The second component, ignore the column with j. We've got 1 times dz dy minus 0 times dz dx. So that's just dz dy. The 0 cancels out the dz dx. And for the coefficient of k, ignore this last column. I have like a little identity matrix here. 1 times 1 minus 0 times 0. That's just 1. Right, so a normal vector, there are lots of normal vectors to the surface, but this is a normal vector. So this is a normal vector. And geometrically, if this vector is perpendicular to our surface, then any multiple of this vector is also perpendicular to the surface. So to reduce the number of negative signs, we can multiply everything by -1. We'll get a perpendicular vector, which is facing in the opposite direction. Doesn't really matter what direction it faces in. Right, so the normal vector we might most often use is dz dx, dz dy, -1. Right, and this is definitely worth remembering. Right? It's going to save us some time when we calculate the normal vector to get the equation of a tangent. And so we should do one more example. Maybe we'll do an example from scratch. Let's see, let's say we want to calculate so find the equation of the tangent plane for the function z, function of x and y. Let's make this one, I don't know, 2x y plus y cubed at xy equals 3, 2. Sure, why not? All right, so what do I need for the equation of a tangent plane? I need two pieces of information. I need the normal vector, and I need a point on the plane. I'll do the point on the plane first. It's a little bit easier. It's going to be 3, 2, f of 3, 2. And so if we plug 3 and 2 into this function here, what will we get? So I'll get 2 times 3 times 2, that's 12, plus 2 cubed. 2 cubed is 8. 12 plus 8 is 20. So our point here is 3, 2, 20. Next, I need to get that normal vector. Again, our life is a little bit easier if we remember that the normal vector can be written as dz dx, dz dy, -1. All right, so let's go ahead and calculate some partial derivatives and evaluate them at those values of x and y. Okay, so first, dz dx. And so the derivative here, x is the variable and y is a constant. So first we have 2xy. Again, y is a constant. So this is a constant times x, and the derivative of a constant times x is that constant. Plus, again, we're doing the derivative with respect to x. So x is the variable and y is a constant up here. So a constant cubed is still a constant. Its derivative is 0. So we have the whole derivative there is just 2 times y. I'd like to evaluate this when xy equals 3, 2. Don't have to worry about plugging in x because there's no x present in the derivative. So I have 2 times 2, which is 4. Excellent. Next, let's go ahead and calculate the partial derivative of z with respect to y. So in this expression, again, we have y is the variable, or this time we have y as the variable, x is the constant. So I have constant times y, and the derivative of a constant times y is that constant, plus the derivative of y cubed with respect to y is 3y squared. We'll evaluate that, again, when xy is 3, 2. What do we get? We get 2 times 3, which is 6, plus 3 times y squared. It's 3 times 4. 3 times 4 is 12. So we'll have 6 plus 12, which is 18. So those are our two derivatives. Right? We could use those to calculate tangent lines, but here we're calculating the equation of a tangent plane. So here, our normal vector, thanks to the observations on the last page, our normal vector is going to be 4, 18, -1. So I already can write down most of the equation of the tangent plane. Right? It's ax plus by plus cz equals d. And the normal vector gives us a, b, and c. So I already know the equation of the tangent plane looks like 4x plus 18y minus z equals some constant d. I can figure out d by plugging in the point. So I have 4 times 3 plus 18 times 2 minus 20 equals d. And so this is 12 plus just 36 minus 20. So I have 48 minus 20. It's going to be 28. So I can now write down the equation of the tangent plane, since I now know what d is equal to. The equation is 4x plus 18y minus z equals 28. And there you have it. That's how you calculate the equation of a tangent plane to a function. Now, as you may recall, I'm a big fan of the philosophy that you learn math by doing math. So let me leave you with a problem to think about. You should try one on your own. So try this. Let's see what z equal f of x comma y. Something that's not too bad. Let's make this, say, 5x y squared. And let's say this is at the point where xy equals, let's make this, I don't want to make the numbers too big, 3 comma 2. Right, see if you can calculate the following things. It seems like a big list. But really, I'm just breaking down into steps what you would need to calculate. So go ahead and calculate these two partial derivatives at this given point. And find the partial derivatives and then plug in the points 3 and 2. And then find the equations for the tangent lines right, along the x direction and then also in the y direction. And the tangent plane. Right, so you'll need to figure out the full point, 3 comma 2 comma what is the point, which is on these lines and this plane. You'll need to use the slope vectors, which we talked about for the tangent lines, and calculate the normal vector for the tangent plane. All right, good luck.